All right, let's jump right in. Today we're unpacking a new theoretical framework called algorithmic thinking theory from Bachany and his colleagues.
Yeah, and the core insight here tackles a really huge bottleneck we see in complex LLM tasks. It's this massive performance gap between what's called pass at one so, a single successful attempt, and pass at k, which is success within k attempts.
And crucially, the paper shows this isn't just about sampling and picking the best one. I mean, when models tackled something incredibly hard, like the IMO 2025 problems, just using a best of 32 approach, it failed miserably. We're talking 30 to 40% accuracy.
Exactly. The model's real power is locked away. It needs to synthesize a final answer, not just select the least flawed graph from a pile.
So the solution here is to basically introduce a formal rule book for this process.
A rigorous theoretical framework, yeah. It's for analyzing these complex iterative procedures, things like reflection or recursive self-aggregation that sort of simulate that slow, deliberate system 2 thinking.
And this theory models the LLM as a probabilistic oracle A. It takes a context C of previous solutions and then samples a new one.
And the success is all governed by a transfer function F, which determines the output probability based on the quality of that input context.
So the ultimate goal is to move beyond just empirical trial and error.
Right, to define optimality and efficiency for these multi-call systems, so we can actually engineer the next generation of LLM reasoning in a principled way.
So let's set the stage here. For you, the listener, this is really about solving what we call grand challenge problems. We're not talking about, simple text classification. This is about generating complex code, proving advanced math theorems, high-level stuff.
Exactly. And when you put these big models on those problems, their baseline success rate, that pass at 1, can be pretty low. But if you let them generate many attempts, their pass at k is way higher. And that gap, that's the gold we're chasing. The knowledge is in the model, but you need an algorithm to get it out.
Right, this is that inference time computation we keep hearing about. You're essentially forcing the model into a slower System 2 process. The intelligence is there, but it's latent. It's hidden across all these different individually imperfect chains of thought.
And we have so much compelling evidence that this works, which is exactly why we need the theory. I mean, think about reflection.
Yeah, that showed the power of just verbal self-critique.
Iterative improvement based on context, it works.
Or that stunning result from the IMO pipeline back in 2025. They didn't just sample.
No, it was a multi-stage process. Verification, refinement, a really strong synthesis engine.
And that pipeline hit an accuracy of 85.7% on that really tough IMO data set. You just can't get there without some form of synthesis. It's impossible.
And then you've got things like recursive self-aggregation, RSA. It keeps a whole population of solutions and refines them by aggregating subsets.
So it's like bootstrapping. You can take partially correct steps from different attempts and merge them into a complete correct solution.
Precisely. So we have all these amazing recipes that we know work in practice, but we don't have the rule book. We lack a formal theory to tell us how to spend our compute budget efficiently.
And what are the fundamental properties of the LLM when it's acting as that reasoning oracle that even make aggregation effective in the first place? That's really the question this paper sets out to answer.
And to build this framework, they start, very simply. The quality of a solution is just binary. It's either a 0, wrong, or a 1, correct.
Okay, that simplifies things. And this lets them define the core mechanic, the reasoning oracle, A. So this is the LLM, but instead of just asking for a final answer, we're asking it to generate a new solution conditioned on a context of previous attempts.
Correct. And the transfer function F is what links the quality of your input context to the quality of your output. So if your context C has, say, 1 correct solution in it, the transfer function tells you the probability that the next output will also be correct.
I see. So the transfer function basically dictates how effective your synthesis is going to be.
Exactly. And based on that, they define the reasoning algorithm itself as this structured procedure of multiple oracle calls. They visualize it as a directed acyclic graph, or a DAG.
That visualization helps a lot. Each node in that graph is one expensive call to the LLM.
Right.
And the length of the longest path in that DAG is the depth. So if you assume, infinite parallelism, the depth is your real-world waiting time. It's the number of sequential steps you can't get around.
And this is such a critical departure from previous LLM theory.
How so?
Well, most prior work focused on the internal mechanisms, right? Like how transformers work or how induction heads enable in-context learning. This paper is different. It's focused on the external multi-call dynamics. It's about how you structure a whole workflow of reasoning, which Previous theoretical models just that largely ignored it.
Okay, so let's get into the central modeling assumption you need to make this all work. The decaying model. Why do they call it decaying?
It's because it captures this really intuitive trade-off between the size of your context and the quality of the signal. The model's success probability is assumed to depend on only two things. First, whether a correct solution already exists in your context, C, and second, just the sheer size of that context, C.
So if a correct answer is already in there, you get a success probability of FC, and if there's no correct answer in there, you get G.
Yep, and the term decaying comes from what we see empirically. Both F and G typically decrease as your context size, K, gets bigger.
So adding too much context, even if it's useful stuff, can just overwhelm the model and dilute the signal.
It's the prompt overload problem, but made mathematical.
That makes immediate sense to anyone who's tried to chain prompts with large models. A huge history can just make the model forget what it was supposed to be doing.
And this idea leads directly to this key theoretical property of monotonicity, which is all about how the oracle responds to better context. They look at two types. First is weak monotonicity. This is sort of the basic expectation. If you give the model a better set of inputs, your output is stochastically better.
So better ingredients mean you're more likely to get a better meal. That seems pretty foundational.
It is. But strong monotonicity is a much tougher condition. It says that if context A is a subset of context B, then B always leads to a better or equal output.
So adding more context is never actively harmful.
Right. And critically, for a strongly monotone oracle, adding more solutions never decreases your expected final score, assuming, of course, the model can actually handle that context length.
So now that we have the math for the oracle, the paper introduces 3 specific algorithms to analyze optimal behavior. We can think of these as like the 3 main strategies for doing this iterative reasoning.
The first one is the branching algorithm. And this is really the gold standard for quality. It generates completely independent solutions and then merges them in a tree structure. The key word here is independence.
Okay, so solutions at any given level are completely uncorrelated with each other. It's like a massive independent peer review process where you only combine the results at the very end.
Exactly. But independence has a massive computational cost, which is why it's a gold standard and not, what everyone does.
Right, which leads to the second, more efficient strategy.
The genetic algorithm. This one reuses solutions from the previous level to cut down on the total compute. This is a lot closer to methods like recursive self-aggregation, where you're iteratively improving a population of drafts.
So the genetic algorithm is the thrifty version of branching. And they note that as your population size gets really big, it starts to approach the same performance as the branching algorithm, but saves a ton on total calls.
And the third one is the random sampling algorithm. This one generates new solutions by sampling K items uniformly at random from all the previously generated solutions, not just the newest ones. It's a way to kind of diversify the context pool before each synthesis step.
And the big takeaway here, which is really the paper's main optimality result, is that the branching algorithm can achieve the absolute maximum possible success probability. They call it X star.
Right, but you only get there if you let the depth of your tree go to infinity. Essentially, independence sets the theoretical ceiling for quality.
And while branching sets that ceiling, the other two can also get there.
They can. They're both shown to achieve that optimal success probability, X star, if you have a large enough number of total oracle calls. They take different paths in terms of cost and speed to get to that same high watermark.
Let's talk about efficiency and cost, because in the real world, that's what matters. The paper looks at the uniform model, where the success probabilities are just constant as long as you don't go over the context limit.
And this model is strongly monotone, which means adding more context should always help.
So you'd think the best strategy is just to use the maximum context you can all the time.
You would think that. But here's maybe the most important insight for anyone designing these systems in practice. The common sense approach, the sliding window approach, where you always use the AAFE most recently generated solutions, is suboptimal.
Wait, hold on. If adding context is never bad, why would using only the newest context hurt you?
Because the sliding window introduces these severe dependencies between your solutions. Think about it. If solution Sn plus 1 is generated using Sn, and then Sn plus 2 is generated using Sn plus 1, any error or flaw in Sn just gets carried forward and amplified. You're creating an echo chamber.
That is a huge insight. It's a mathematical confirmation of what we've all seen anecdotally. Just sequentially refining something can lead to the model getting stuck or overthinking its way down the wrong path.
Independence is crucial because it breaks those negative correlations.
So when we compare the efficiency of the three algorithms, what's the trade-off?
It's massive. The branching algorithm has the fastest convergence per step. It's logarithmic. But because you need to generate so many independent solutions, the total number of model calls just grows exponentially.
So it's the highest quality, but by far the most expensive strategy.
Right. Whereas the genetic and random sampling algorithms offer much better computational efficiency in terms of total cost. They have polynomial convergence, so they're much, much cheaper overall, even if they take a few more iterative steps to reach that optimal quality. The genetic algorithm in particular gets you like 99% of the way there at a fraction of the cost.
Okay, what about those more realistic decaying models where bigger context actually hurts performance?
They studied two types. With exponential decay, where the signal degrades really fast as you add context, the optimal strategy is to use tiny contexts, often just k equals 2. If the decay is too bad, the process isn't even boostable unless your base quality is already pretty high.
And if the signal degrades more slowly with polynomial decay?
Slower decay lets you boost performance much, much faster. There's a theoretical scaling algorithm that can use a context size that scales inversely with your base error rate. And this lets it achieve near constant success probability in just O log n iterations. That's incredibly fast convergence. It suggests that if we can build LLMs with slower decay rates, we could build vastly more efficient reasoning pipelines.
Okay, so we've got the math and the theory. Let's connect this all back to the real-world evidence that grounded this paper from their experiments using Gemini 2.5 Pro on the AAME 2025 dataset.
Yeah, the data gives really strong support for both the decay assumption and the synthesis capability. For decay, they showed that even when you fix one correct solution in the context, just increasing the number of incorrect solutions dramatically lowered the model's accuracy. For one of the math problems, correctness fell from almost 95% down to about 50%.
So more context really does equal more complexity and degraded performance. It validates that whole decaying model idea.
Right. We know the models suffer from this signal dilution. But the second experiment confirms that the synthesis engine is incredibly strong.
Okay, what did they do there?
They fixed the total context size at 5 solutions, and it just varied how many of those 5 were correct. And the model's correctness it's smoothly and significantly increased with the number of correct inputs.
Oh, wow.
Yeah. For one question, the base accuracy was 49%, but when it was synthesizing from that context, the weighted average shot up to 89%. That massive 40-point gain proves the LLM is actively using the context to build a better solution than it could on its own. It's a strong verifier and aggregator.
So if synthesis is the goal here, what are the current limitations of this theory? Where does it go next?
Well, the binary quality model is a huge simplification. Real-world reasoning has degrees of correctness. So future work has to incorporate partial solutions. And maybe more critically, it needs to incorporate answer diversity.
Right. I think about that all the time when I see people aggregating code solutions. Combining two partially correct pieces of code only works if they solve different complementary parts of the problem.
Exactly. The paper suggests you could model diversity by associating like a unit vector with each solution. And solutions that are orthogonal, so vectors pointing in totally different directions, would imply complementary, non-overlapping information. We want to aggregate the most diverse, high-quality information we can find.
So this whole analysis gives us these rigorous bounds on what's theoretically possible and confirms that the best reasoning algorithms are going to favor independence and rapid convergence. But the practical challenge is still that same trade-off between quality, speed, and cost.
The total cost of inference is what matters in the real world. We know the branching algorithm hits that optimal X star the fastest per step, but it costs the most in total calls.
So the final provocative thought for you to consider is this. Given how expensive these inference calls are, how do we design reasoning algorithms that cleverly exploit massive parallelism, running many independent lines of thought at the same time to get those logarithmic speed savings, while still minimizing the total number of expensive model calls and avoiding those dependency traps of simple sequential refinement? That efficiency problem, that remains the central challenge for applied algorithmic thinking.